Yeah, thanks everyone for attending this event here at AIMEN. It's really a pleasure for us to host you here and to organize this training in the frame of the AMBIANCE project. I really hope that you will enjoy the very nice talks and have fruitful discussions along the day. Yeah, thanks for coming, and I really hope you have a good time here today. So, Giulio, want to? So, thanks.
Okay, thank you all for being here. So this event is organized in the context of the AMBIANCE project, which is a project which started 4 years ago and will end this month, and is in the context of urban development and sustainable urban development. In most of human history, people tend to live outside of cities. So this is the first time in history in which the majority of human people live in urban spaces. And it is projected that this trend will continue by 2050, almost 7 billion people will live in city. So it is quite important that the urban development is guided in a sustainable, resilient way, so that this will contribute to the sustainability and to the sustainable development of the whole society. And in this context, the AMBIANCE project try to address all problem of development in urban spaces through new environmentally friendly materials and products, and new digitalized processes. So AMBIANCE is in the context of the so-called twin transition, the environmental and digital transition together. From the product side, the idea is to develop new bio-based products which have the same characteristics of oil-based raw materials, because a bigger problem of the adoption of bio-based products is that you can make them, but they are usually either more expensive or with less performances. So the AMBIANCE goal is to have products which have the same characteristics and properties of original products, and to use the digitalization to optimize the processes, in particular in this case the processes of extrusion, large-scale additive manufacturing, and compression molding, to optimize them in such a way that they are efficient and sustainable. The products that AMBIANCE have developed, and you can see them also outside of this room, are the artificial turf and filament of the Mondo use case, so using, for instance, force field and so on, and this is done through extrusion of bio-based material and biothermoplastics. Then a second use case is the realization of street furniture, and this is the use case of Setga, made by large format 3D printing, and in this from bio-based materials, and in this use case AIMEN has a very big role. And the third one from the Swedish company Podcomp, is the realization of decorative panels for the construction of buildings and other objects made by compression molding using agricultural waste streams. And the digital technologies that are used, and that will also be discussed in this training more details by the speakers, physical simulation of molecular dynamics, parameters and properties, or the use of machine learning models to identify the relation between parameters and optimize the processes, and the hybrid digital twin that join the simulation and the machine learning, and also use data taken from non-destructive testing to have an efficient model of the process. So some of the challenges that the process had to solve to give us the result are the resistance to weather, because these are objects intended for outdoor use, so that must withstand rain, wind, frost, and must have a long lifespan. Then to guarantee that at the end of life, these processes are either recyclable or reusable, because biothermoplastic made of bio-based products solve the unsustainability of the manufacturing phase, but not necessarily solve the end-of-life sustainability. So one needs to develop something that is recyclable or reusable. And the third one is the actual implementation of the digital models. Now, some of the results will be discussed more in detail in the speaker presentation. I give you some example here. So in the SETGA use case, the street furniture AIMEN and SETGA could demonstrate that the plastics used for the furniture has only a slight color deviation after exposure, so it can be used outside where there is sun, and it will not lose its aesthetical properties. And this was demonstrated also both in a climatic chamber and in real exposure, and you will see them outside tomorrow. And also for the Mondo use case, the artificial turf was shown for the infill, so the part that is not green filament, but the parts below, it was shown that has a high rates of biodegradability, and that the filament is also recyclable. For the optimization part, also it was possible to implement a new system to have some data acquisition, high-speed data acquisition, monitoring, and analysis of result by exactly measuring the filament, measuring the filament profiles to have also information on the manufacturing process. And for the AIMEN, for the SETGA use case, AIMEN was able to develop a real-time temperature monitoring system that could efficiently monitor the deposition of the additive manufacturing deposition of the bioplastics. And AMBIANCE, okay, it is an European research project, so it has as a goal, as I said, to develop processes and digital processes. But there is like a third pillar, which is the impact valorization. So all the action that are taken to not just have some research results that do not have any impact on society, but to do whatever we can so that results from a research project can contribute to the whole society. And this is something. Something where my organization Create is more involved in this part. So the part on promoting the project result and disseminating among a larger public. Also then to handle and to study how to have a commercial exploitation of this result, because the goal here is not to have a proof of concept, but to have something that can then the manufacturing companies of AMBIANCE can actually use and sell. Then also to have a collaboration with other European projects that are doing similar things. So we had this cluster of all projects dedicated to use bio-based material and digital processes for different use cases. We had all activities together in such a way that we could have a network and we could promote a larger action. We also did some activities of standardization where we developed guidelines and standardization documented on the durability of bio-based material against external use. And finally, there is the organization of training to promote the dissemination of skills needed for the green industries. We did last year an event in Modena on LCA and eco-design. And today we are doing this event here, which will have 4 modules. So from project partners, ITA, SUPSI, RECENT, and AIMEN. And we will discuss what I now just slightly touched more in detail. So I just touched very briefly how these technologies were used in the AMBIANCE project. You will see a more deep analysis on what are these technologies, the physical-based simulation models, the LCA specifically for bio-based product for 3D printing and other application, the part of doing non-destructive testing on bio-based material, and how to evaluate sustainable material for the process of additive manufacturing. You will see the theory more in detail. You will see some application on the AMBIANCE project from the partners who developed in the AMBIANCE project. And tomorrow there will be a showroom in Pontevedra, close to here, so where the AMBIANCE solution will be installed in a public square, the Plaza de Barcelos. I invite you all to come and to see the product tomorrow. So you see a small demo here, but you will see them on a larger scale. And you will see outdoors, so where you will see that they are actual real products that can be used in outdoor urban spaces. And with that, at the end of the training, we will share with you a satisfaction questionnaire, so that you can tell us if you like this training. If there are something else that you want to know, and with that, I leave the floor to Manuel from ITA for the first presentation on physical-based simulation. Thank you.
Okay. So. First of all, thank you everybody for being here attending this training, and thanks for AIMEN especially to allocate the installations and provide the infrastructure. So I'm going to start with the first module of this training. I just give some minimal explanation of what is this, because the first module is dedicated to the use of physical-based simulation models and reduce order models in manufacturing processes. So just what is expected from this training is explain a little bit what is physics-based simulation, what we understand with this concept, and especially how we have used these techniques, these tools, in the framework of the AMBIANCE project. That as we have seen in the previous presentation, we have several manufacturing processes involved to manufacture these pure urban furnitures and stuff. We will explain case by case on how we have made the application of these tools. And also we will discuss a little bit how to compare the physical-based simulation models into reusable models that can be integrated in digital twins or in support tools for the process operators. So basically, as I mentioned, we have several points, but the main one is how we have applied this manufacturing simulation technologies in the framework of AMBIANCE. We will combine a little bit of more deep theory or with mainly application examples to see the process. And we will finish with some hints of integration into digital twins. So basically, what we understand by physics-based, in a nutshell, physics-based simulation is the use of simulation tools that replicate what we observe in the real workload of the processes mathematically, describing what are the underlying physical phenomena inside the processes, like mechanics, heat transfer, fluid flows, chemistry, etc. And what is important for manufacturing, basically because all of these processes are governed by this type of physical effects. So sometimes it's interesting to have insight on these processes because experimental can be costly or time-consuming, or we have limited access to some certain variables in the process because they are difficult to measure or impossible in some cases. So the simulation is expected to give a support to get more in-depth understanding of the process and to make virtual scenarios to predict some magnitudes using these tools in a virtual environment can help to pre-optimize parameters or to at least understand sensitivities. And this, in the end, is expected to reduce the trial and error on the experimental side. So what we are done in the framework of AMBIANCE. So the first use case is the artificial tough filament stretching in the Mondo manufacturing plant. Here we have quite a scheme of what is the process. The process starts with the instruction line that has some material coming in that in the form of pellets of plastic that are extruded, and then there are cooling. It goes to the stretching part, what is the one that we have focused on, this simulation stuff that is composed for some goddets that are wheels that are controlling velocity and temperature and make the filament pass over an oven, different ovens at different temperatures, and controlling the velocities of these goddets, we control the stretching imposed to the filament. So what we have done here is to try to focus on this stretching process. We have several physics involved behind. Basically, in this case, we are dealing with the large deformation of polymer melts and solids in this transition. This is in the field of continuum mechanics from the simulation point of view, where we have a strong dependence of properties on temperature. That is something that we need to take into account. And also we have what we call geometric nonlinearity. That means that we have a lot of deformation to be modeled that is suffering material from the beginning of the stretching stations to the end. So more or less, I'm going to follow the same scheme for all the use cases. Some brief notes of what we are doing here to develop these models. First of all, we need a geometry. And in this case, we are taking the filaments at the end of the structure. So we obtain this section just after the extrusion, and we convert this into a finite element mesh to be used on the process. And here, probably the most interesting thing is that the characterize the material behavior, because it's in this case we need to perfectly reproduce the viscoplastic behavior of the material. That means that we need to characterize at different strain rates. These strain rates are typical from the velocities we have on the objects of the project, and also the dependence on temperature. The range of temperatures and the range of strain rates are selected to be to cover the expected ranges on the real processes. This process has been repeated in the project AMBIANCE project for several materials and several combinations of bio-based materials. So we completed this characterization in order to model the behavior. Then we need to put these boundary conditions to the models, and this is what the work here is to simplify the reality into some conditions that we can impose directly to the models. In this case, the conditions is just the stretching velocities and the stretching quantity that is controlled by the object's velocities. So we transform this into displacements and velocities for the model, and also the temperatures in the process. Now here you have, for example, representative results of one of these simulations. The advantage of these physical video simulations in this more high fidelity models is that we have access to many variables. In particular, we have the full fields of stresses, strains, displacement, etc. But in the case of this project, our focus was on the dimensions, the final dimensions of the filament, characterized by the width and the height of the filament. Once we have the model set up, is the time for the exploitation of the model, and we do this by means of a simulation theory. This requires to define which are the suitable ranges for all the velocity of the objects, and to establish a DOE strategy to create the DOE matrix. And here we are quite dependent on how heavy or how costly is our simulation model, and the number of parameters we need to cover the design space for this manufacturing. So here, depending on the case, we use more or less simulations, but in order to be efficient, we need to make automations on this simulation process in order to generate the different models, changing the parameters, obtaining the results, and printing the results in some files or data frames that we can use afterwards. And here we have one of these results. We have all the data frame, then we go to the ROM building. That means we need to build a model that is much quicker than the full simulation model, but retains the important results, the ones that we want to use afterwards. In this case, for example, we have two results: that the height and the width of the filament, and how they depend on the object's velocities. Analyzing this type of graphs, we are able to say which are the variables more important, which have the most effect, and which are less important. And not only the importance, but also the true end, in which direction they affect to the result. So basically, adjusting a ROM means that you look for a model that minimizes the error with regard to the DOE-generated data, and you can use it afterwards. So that's why we always take care of the error metrics. They give us which is the quality of our ROM reproducing the full of the model results. So that was one of the cases. That was more or less one case that is mechanically dominated. Now we go to the second case that is related to the large format additive manufacturing use case for manufacturing urban furniture. In this case, the process is basically is a large format printer composed by a robot extruder that melts the polymer and executes some toolpaths predefined to build layer by layer the geometry. In this case, we have divided the process in 3 different aspects to be covered by the modeling approach. We have a model that is focused on what happens inside the extruder, where the material is conveyed, is melted, and then is extruded through the nozzle. So this is our first model. The second model is dedicated to do what happens in the very last portion of the extruder, that is the nozzle, and the interaction with the substrate. The substrate is where you deposit the melt polymer. And finally, we are another model that is dedicated to the building of the component itself, the furniture or whatever. So what are involved physics here? So as I mentioned, we have a melt flow. So we are going to use CFD simulations and dealing with a non-Newtonian high viscous polymer inside the extruder and through the nozzle. We have a free surface flow. That means that the surface, the melt polymer exiting the nozzle is in contact with the substrate, but on the other side is contact with the air. So it takes some special boundary conditions. Of course, everything is dominated by the rheology of the material that is high dependent on temperature and shear rate, and also the deposition kinematics that couples the extrusion rates and the motion velocities of the rod. And finally, very important is the heat transfer phenomena that determines how would be the adhesion between the layers. So let's go for the first one. The first one, we have made a model, simplified model of the inside part of the extruder, everything that is inside the barrel and the screw. We have a model for this. The material properties for this type of simulations are experimental rheological curves that have been made by AIMEN. Here we are simulating the rotation of the screw inside the barrel at a steady state regime. So the flow is laminar. And here we involve several conditions, boundary conditions. First of all, the couple of flow rate AMBIANCE. This is a relation very important in extrusion. So we impose one to wet the other. Also, we have a condition at the end of the extruder where the nozzle is allocated. We need to provide several possibilities of incorporating different nozzles of different diameters. That means different resolutions, and also the temperature. The temperature is representative temperature averaged on the extruder. And here we have typical results of these simulations. One of these simulations. Basically, we have full access to the velocity profiles. So we have full access to the pressure distributions, like in this one, where we see that the pressures, maximum pressures are in the zones at the end of the screw, where the channels are very narrow. Shear stresses, that we can obtain histograms of the shear stress distributions and strain rate distributions in order to see if our characterization
Sí, pero no
test.
pasa nada.
Y ya creo que va. Ahí hay libros rutinas que hay que arrancarlas.
Ah,
Y son aquellas que están en paralelo.
Yeah. So next step is, as before, we need to define some ranges.
Sorry, you lost the share. No, sorry. Continue.
It's okay?
Yes.
Okay. So next step is to define the ranges. In this case, we have followed the data from the rheology, and we have extended to cover a little bit more of range on temperatures. We have analyzed the full range of flow rates for the extruder, and we have assumed some levels for the pressure loss at the end and in the nozzle in the gap with the layer. As before, I'm going to not to explain more now. We train a model, the reducer model. In this case, we are using a RDF approach. That means it's a radial basis function. And here we have the results in terms of sensitivity analysis of all the parameters to the all the variables we have in the model. Basically, this give us information on the tendencies, the relative importance of the several parameters. Next one is the nozzle model. Nozzle model, I have mentioned, we use again a CFD simulation software. We use the same characterization of the rheology of the polymer melt as before, but we are focusing on what happens on the very last part of the extruder. That is this green part, that is the nozzle, and the layer thickness on the substrate. That is also a restriction for the flow that needs to be taken into account for the pressure loss prediction. And here, the boundary conditions, the process that is are the flow rate, the layer height, translation velocity of the nozzle, and also extrusion temperature. Here we have a couple of simulations, animation of this type of simulation for two different diameters of the nozzle. We can see more or less in detail what is the process and what I mentioned before about the free surface. So we have a translating nozzle in this case, and the top of the filament is free in contact with air. So this needs a special boundary condition. We can access, as before, to the full distributions of pressure or velocities. But in this case, we are quite interested in the resulting section of the filament that we can parameterize very simply in a simple way by the height and width. These parameters are extracted from every combination we will make in the simulation. So as before, we define a DOE. In this case, we cover the different diameters that has been used on the real fabrications, and we parameterize as a function of this diameter, because on additive manufacturing, there are several ranges that recommended for the height and the width of the filament as a function of this diameter. Also, we cover the velocity ranges that we can afford. That means that in the end, if we define the height and the width and the velocity, we need a flow rate. But this flow rate needs to be between certain limits. The limits are the limits of the extruder. And also the velocity is controlled and is imposed in several limits. So for all of these simulations or this combination of parameters, we check the flow rate and we analyze we drank the limits to be inside the extruder limits in terms of flow rate and for the ranges of the velocities. That means that we are covering all these suitable range for the velocity. Next, we have the ROM building time. As again, we are using again a radial basis function, and we have a new model, a new piece of model that covers this nozzle for different heights, layer heights, and widths of the filament and flow rates and velocities. Finally, we go to the printing phase. Here we are building the part, so we need the geometry of the part that we convert in a mesh. And here the simulation type we are going to focus is a thermal simulation. We are interested in predicting temperature distributions over the full process. So basically here we need the path planning to be simulated. That is the input for us, where all the trajectories and velocities are defined. And we convert this into the simulation models in a finite element code, like a success simulation of events. Events are how these positions are moved along time and which layers of material are added in every movement. So here, for example, we have one of these simulations for one of the earlier test demonstrators performed at AIMEN. Here we can see how it's building layer by layer this part, this simple part. The representative results, we can see temperatures. What we are seeing now in the screen are temperature distributions at any time, at any point. So in particular, what we are looking for is to predict the temperature in a point of one layer when the next layer reaches the same point, which is the temperature it finds on this substrate, because this will determine the quality of the adhesion between the two layers. We can see here one graph that is quite representative. So the material is deposited in this point at the extrusion temperature, and then it's cooling because it's transferring heat to the ambient by convection, by conduction through the material, till the next layer appears. When the next layer appears, it jumps again. So we are interested in this minimum point because it will determine the quality of the adhesion. First of all, I have to mention here that we have in the model some parameters that need to be adjusted, because not everything depends on material properties. There are a couple of parameters related to convection that cannot be obtained from the material diagram. So we need some tests to adjust this coefficient, convection coefficients, and if there is any heat source like radiation panels or so on. So we use some tests that were performed at AIMEN in different conditions that we have here, conditions changing the height, the printing speed, and we compare their measurements of the temperature monitoring with our predictions. And we run an optimization in order to fit what was the best combination of these coefficients that approaches to the real of the test. Once we have these coefficients, then we can simulate the process of the furniture. For example, we have here one of the simulations of one of the furnitures. This is one informative panel to show something on it's a support for this informative panel. And here we can see how it's building, and again, layer by layer, and how the temperature is evolving continuously over the time. And again, we have here the typical curve where we analyze the temperature drop at the cooling between one layer and the next one. Here, for example, we have used this model to analyze what will be the effect of changing the printing velocity to slower velocities to higher velocities. And we can see here the effect. So our base simulation would be the orange line. And if we go to a quicker simulation, a quick impression, we get higher temperatures on the substrate. If we go at a lower velocity, we have very low temperatures. In this case, for the material we are using, AIMEN determine a processing window that recommends to have this substrate temperature in a certain range, around 160 degrees. So we can analyze by simulation what would be the velocity required to be in this range. The problem of this simulation, for example, for this part, for this furniture part, that is the informative panel, is that they take long. Just to give an example, this simulation, as we have seen, it took 80 hours to run in a server, just one combination. So in this case, it was not feasible to use this very heavy, very costly model to regenerate a DOE of simulations, because it will take much longer. So we take a different approach. Based on what we have seen before, we can see that the temperature is not is different in every point, but mainly governed by the position in the set direction in the printing direction and by the time, not really by the trajectory. So we have a simplified model that just builds a portion of this wall in height, and in this model we can parameterize all the dimensions in terms of thickness of the wall, thickness of the layer, and everything related to the printing process, velocities, temperatures, and so on. We also introduced the infrared heating on the top of the filament that is solidary with the nozzle. And then with this type of simulation, we can see the representative curve we are seeing. We can see the new peaks that are because of the infrared heating. We can see here that the material, once has been deposited, suffers a small heating. That is when the posterior part of the lamp is heating what has been deposited. And then also when we have reached the substrate temperature, then the infrared, before printing the new layer, is heating again, and we have this jump in temperature. That is the effect we are looking for. Temperature of the substrate before the new material comes. So more or less these two jumps are quite similar in magnitude, and in this case, this is the point we are interested to be extracted from the simulation. Again, we generate a DOE. In this case, was a larger DOE. We managed with 7 parameters, combining geometry, dimensions, temperatures of the extruder, temperatures of the bed, the infrared heating, speed, and layer time. So again, we built the ROM, and we have one model that gives us results for different layers, heights, and also we have the possibility to obtain different points of the temperature, different points of the bead in the center or in the side. And more or less, this will cover the full simulation models for the set values case. In this case, it's required an additional step, because all these models we have been seen before are like building blocks of parts of the process, relevant parts of the process. But to make it they run together, they need to be orchestrated. Orchestrated means connected, because some outputs from one of the models are inputs for the next one. And everything needs to be connected to the parameters of the printing process. So this is a top layer where these models are orchestrated. and make work together. Okay, so let's go to the last use case. In this case, is the thermoforming or the compression molding of bio-based panels in the PODCOM use case. In this case, we are dealing with a mold that comprises the powder material coming from the biomaterial sources in more or less powder-like way, and they are converted by the application of temperature and pressure into solid panels. Here we have been focused on the thermal behavior of this compression process. So we have again a heat transfer process as involved physics that are governed by the conduction of the heat on the mold and the thermal exchanges with the polymers panel, and also polymer in this case is bio-based material, and the ambient. What we have here is more or less what is the distribution of components inside the mold. The important thing regarding the process condition setup is that we have heating elements. So heat elements are electrical cartridges that are in charge of heating the mold to the searching temperature. So our models have been incorporated these heating elements, and we have the possibility to change the power supply to every one of these heating elements. As representative results, we have the full distribution of temperatures in the full mold, on the cavity surfaces, and even in the panel. In this case, our interest on this type of models was to quantify what is the degree of temperature uniformity that we can reach in the model, in the process. So the objective was mainly to determine these gradients on the surface of the cavities, and that was why we prepared this thermal model. Again, in this case, we covered a very wide DOE of simulation. We performed more than 2,000 simulations because we have many input parameters. Basically, we have 12 heating elements and a constraint that is the total power supply that we keep under control in a certain range. I want to stop a little bit more in this use case because it's interesting. It's different with regard to the other ones because we have used a different technique to make the room building. In this case, we are not interested in punctual values. We are interested in the full distribution of on the cavity surfaces. So we use a different technique that is called proper orthogonal decomposition in combination with singular value decomposition. That consists more or less in an algebraic process that takes all the simulation we have done in terms of temperature results for all the nodes of the simulation of the cavities of the surface and organize in a matrix, and then we make a decomposition of this matrix to obtain what we call the orthogonal modes. Orthogonal modes are like ways that the temperature can change in the domain. And also we have the singular values that are giving us the importance of this mode. So if we have 2,000 simulations, we can potentially have 2,000 modes. But the good thing at least are that only a few of them are relevant. So we can trunk all the matrices by selecting a number of modes based on the value, on the singular value of this mode. So what we do is to trunk all the matrices, and then we have a training that is making a linear regression between the powers we have supplied to in the simulation with this trunk matrix for the determination of new combinations. In the end, with just matrix operations, we're able to predict the temperature in every point of the cavity, in the top surface and the lower surface, just in few milliseconds. That takes the operations to be performed. Okay, so let's go to the integration. We have seen here several pieces. One of the ways to make this available for use is to integrate this into tools like user tools that the operator can change parameters and obtain predictions. I don't know if we have time to make a little demo how we are. So basically, we have here one of these building blocks, in particular the thermal ROM for the 3D printing models, and we can here select one of the variables, for example, the temperature on the substrate, and we can show the influence of this parameter. So if we are in this point, we can see how, in this case, the temperature on the substrate is affected by the different parameters: the height of the layer, the heat of the infrared, the time of the layer construction, and velocities, etc. So what the operator can do is to change whatever parameter, just scrolling, and you can, the interface more or less allows the user to change any parameter and to get instantaneously the temperature that we want to see. We can also define some tolerances. For example, I can select the tolerances. I want to put here the limits, the recommended limits for this temperature in a range. And we go back. So if we are below the limits, we get alerts, and we can try to move to get this in the right direction. But you have information on the graphs. So if you are in this point, you want to have more temperature, you can see the parameters in which you can work. For example, I can reduce the layer time, making the robot going quicker. So we can reduce this, and we can obtain instantaneously the new solution. Not only the solution at that point, but also all the neighbors, in order to move, because these graphs are dynamic, are not the same for any point. You can see that they are changing their sensitivity depending on the point you are. So you can work with the infrared heater, for example. Now in this combination, we are already in the range, the desired range. So this is more or less what would be the use of this tool for an operator to make virtual trials. Okay, so let's change again to the presentation. Okay, so this was the first possible use of ROMs, how to take profit of them in a manufacturing workshop. The next one is to not making manual trials, but connecting them to the monitoring system. That means that the digital orchestrated model is connected directly to the streamed parameters from the line. In this case, it takes certain parameters of the line and takes them as input for the models. And then they provide instant predictions as outputs for the models for every single point we have on the frequency that we have used on the channels, on the monitoring system. So basically, this is a capture of one of these manufacturing processes where we have some noise of the signal and we have some changes of parameters at certain point on the process, and then the model is evaluating the responses in terms of width of the filament, the torque, and the pressure as a function of all these variations on the process. So this is the second possible use, connecting to the monitoring systems to create this digital twin infrastructure. Okay, we're at the end. A summary, more or less, what is physical B simulation, how we exploit in DOEs, how we convert into reducible models that runs on the fly, and how this can be integrated into decision support tools or directly into digital twins for quality monitoring, making this run connected to the line. Basically, the difference of these two types of usages is the first one, the integration in the design support tools is basically for virtual tryout, make a lot of virtuals in very few time in order to better understand the process. Because we see the result, but not only the result, we see dependencies and how further changes on the parameters would allow us to modify the result as we want. This is the trend analysis. I have not mentioned that these engines can be also, these models can be integrated into optimization engines to make the search of best parameters in specifying targets for the outputs. And also it's useful as training tool because for a new process, we can have the feeling of how sensible will be to the parameters for every new geometry. And the second use is more related to the monitoring system. So it allows us to translate fluctuations in the process or changes in the process into estimations of the quality. And it allows to define virtual sensors that we have. A virtual sensor is a prediction of certain magnitude or certain variable that we cannot access through real sensors. And the powerful of these approaches is that combine quite well with the machine learning approaches because they are have different advantages and disadvantages, and when combined with data-driven models, they can be synergically looking for to obtain the best results. So that's the concluding remarks. The physics-based simulations are provided a deep understanding of the process, in this case, manufacturing processes. They require the use of multi-physics simulations because many of them involve different physics at the same time. And the use of reducible models allow us to make this available to be used in real-time processes because we reduce drastically the computation time. And this is why, in this way, we can integrate in approaches like we have seen before in decision support tools or in digital tools. Okay, so that's all, and thank you very much for your attention.
I have some question, Manu. When you do this physical-based modeling, do you need the parameters of the material itself?
Yes.
But for instance, I think all of the material for the three use cases is composite. It has a lot of interaction between the fillers, reinforcement, and the matrix or binder. Did you consider that in the simulation?
Well, the simulation can be set up for depending on the interest. What we have seen here is not considering that scale of the material that composed of the micro constituents or nano constituents, because we have been focused on the overall process. So for us, in these simulations, we have seen the material is like an homogeneous one or homogeneized one. Okay. But of course, there is the possibility going into micromechanics simulations to consider this type of effects. But it has not been the focus of what I have shown here. But of course, it's a possibility, and we do in other projects. It involves considering the material as an heterogeneous phase, and then you can use micromechanics simulations or discrete element modeling if you want to see how the particles are moving and interacting between them, or even going down. We can go into molecular dynamic simulations that we have done at the beginning of the project, that was not for manufacturing purposes, was more for material design. But the response is yes, we can access to this type of constituents effects, but has not been shown here today.
But when you consider the material system or the composite system, is it anisotropic or isotropic? You consider it?
In our case, has been considered as isotropic.
Which case you mean?
In your case, in Portcom. So, yeah.
You consider the isotropic case?
Isotropic, yeah. So for us, the panel is isotropic material with certain averaged properties. Okay. So, but I think in that case it's not relevant because more or less the thermal behavior is governed by the mold. The mold is still is isotropic, hopefully, and more or less is controlled by the mold kinetics or dynamics of the heating behavior.
I see, but I think you maybe in the future work or continuous work, we need to consider interface between the tool and the material. Yeah,
the interface of the tool in the material is considered in the simulation by a constant contact resistance, because there is a jump between the temperature on the surface of the mold and the temperature it really sees the material. That is considered by a numerical parameter that takes into account this jump. It's a contact resistance, but has been taken as a typical value. So the possibility to account for anisotropy in the material would be to have a definition of the material like orthotropic, for example, but that we can change the conductivities of the material according to the direction. Probably in your case, you have more or less random distribution of whatever fibers in the plane, but you probably have different material behavior on the thickness direction. So that could be taken into account in the model, just changing the model definition. Instead of using isotropic, we could use orthotropic and assigning different properties.
I think the situation in our case is quite complicated because we really, the main part of the material is a straw of the plant. So it's kind of either hollow structure or something. It is not really like a composite or blend that you have a lot of almost half of the matrix and the fibers, yeah, or the fillers.
Yeah, I think that was one of the motivations that we changed a little bit the strategy of the simulation. So we focus on the thermal part of the mold.
Yeah, exactly.
And we give this to you.
No, but it's a good strategy because our case is actually, if you the constituents in the constituent terms, it is actually simple because we have just, let's say, if you want to say it just have one material, because that's a straw. But if you look into the material itself, the straw is very complicated itself. Yes.
We have been simulating this type of processes, not for the material you are using, but for example, for board material table boards made of wood.
The particles.
Yes, and we try to model this type of processes with using discrete element modeling, interacting all the particles and compacting all the particles. Within resins inside to bond them.
It is different because like the particle board, you use a much lower pressure because you have both heat and rising and also some pressure. But in our case, it's mostly facilitated by the pressure and the moisture together and the temperature.
Yeah, I think this applies to everything. You can try to model practically everything that has clear physics. Behind the question is if it makes sense. By the effort you need to invest on this simulation, on the characterization associated to get the real data, and the outcome you will get from the simulation.
Yeah.
So basically, there is a work to be done at the very beginning, is that to establish which is this equilibrium, the fidelity of the model you want and the scope of the modeling you are going to develop.
Exactly. Last comment.
Yes, sorry, does anybody else have another question? Sorry, we have
No, it's okay. It's not a question. It's a just comment. Our process is compression mode. It's not thermoforming.
Okay. Yeah.
Sorry.
Yeah, I think I got wrong. Yeah.
Thank you.
So, thank you very much.
Hello everyone, thank you to be here also from our side. I'm Marco, and with me there is Valentina. Let me just introduce a little bit this module 2, that is the focus is LCA of bio-based material for especially 3D printing, because we would like to connect our topic with what we see before us and what we will see in the module 3. So just let me quick walk you through this presentation. We start with a little presentation, our laboratory, our competence, what we basically have been in Ambience, and then we go more in detail about bioplastic and bio-based material, especially considering the LCA analysis, so how we can perform analysis, and which are basically the technical and the methodological challenge and barrier that we figured out also thanks to Ambience project. And Valentina will, she will, let's say, introduce and give our expertise in this topic. Finally, we will see technical use case, and we will present you also our tool that we developed also thanks to Ambience project that is called Greta. Just as I said, a quick introduction of our laboratory. We are two research in SPS laboratory in SUPSI. It's a university based in Lugano, the Italian part of Switzerland. Our activity in Ambience basically focused, as I said, in our agenda, prospective LCA of new bio-based material. So basically, it's not just a normal LCA, because when we develop a new bio-based material, it's something really also from our perspective. So the sustainability expert try to perform an LCA, so an analysis that give us real the impact of this new material, considering also that the benchmark, the data from database are not always available, because it's a new material, so it's something reasonable. And then we go, especially in this case, in certain use case, and we would like also to present our real-time sustainability platform that's called Greta. In Greta, thanks to Ambience, we developed some function that basically help us as a sustainability expert, but also especially the user, the designer, the people inside also the use case, understand really how this new material can perform compared to the fossil, the base one, let's say, and also how they can also improve and change a little bit this material in order to enhance step by step the performance in terms of environmental, but also cost or circularity, what they need basically. Just a quick overview of our laboratory competence. As I said, there's a sustainability production system laboratory in SUPSI. We are quite a big laboratory in SUPSI, because we are responsible of bachelor and master industrial engineering thesis, and we are basically at the moment around 30 active project, European project, considering also Ambience. We are almost 50 employees. So the main competence is develop a tool and a methodology in order to assist and enhance, I would say, sustainability in production system. Of course, production system for us is just the process, but also the product. In this case, we can develop with the use case in order to find new material, new product with the better environmental performance. I leave the floor to Valentina that give us.
Okay, so before starting speaking about what is LCA and how to apply it to the bio-based material, I want to introduce some basic concepts So I want to distinguish what are bioplastic and what is a bio-based material, because usually these two words are used together, but they are different. So according to European bioplastic, a bioplastic is a material that is bio-based or biodegradable or both. So bio-based and biodegradable are two characteristics that are different and independent. So what does it mean, bio-based? Bio-based means that a material came from the biomass, so basically from plants like corn, sugarcane, or wood, and it can be composed entirely with the biomass or just a portion of it. And then biodegradable is a characteristic of the material, so it's a biochemical process in which there are some microorganism that converts the material into water, CO2, and biomass. What is the most important biodegradation process is that the right conditions are needed. So there should be the right temperature, humidity, and so on. So all this information are important because we have to know that there could be some bioplastic that are bio-based but not biodegradable, and some bioplastic that are fossil-based but biodegradable. So to classify the bioplastic, we have three categories. The first and most common category are bioplastic that are bio-based and biodegradable, like PPLA. So they are composed of biomass, and at the end of life, they can decompose, can be compostable or biodegradable. Then the second category are the plastic that are bio-based but not biodegradable. An example can be the bio-PE and the bio-PP. So these are materials that have the same chemical and physical characteristic with the conventional plastics, but at the end of life, they have to be managed, treated in the conventional sites like recycling, incineration, and landfill. And then the last category are fossil-based but biodegradable plastics. So these are like PBAT. So there are bioplastic that not derived from the biomass, but from oil. So they usually have limited environmental bounds compared to the other bioplastic style. What is important to know about the bioplastic is the biomass origin. So we can have basically three generations of feedstock. The first one is the first generation. So this category are bioplastic that are generated from food crop, like corn, sugarcane, soy, and so on. And which is the problem of this bioplastic? The problem is that there is the risk of competition with the food supply, so with the land use. So sometimes there is the use of land that before was used for producing, let's say, food crops, and then reused to produce bioplastic. So this is the main problem. Then we have the second generation feedstock that are like lignocellulosic waste and crop residues. So this category is preferable to the previous one because there is no competition with the food supply. And also they are preferred in terms of LCA performance because they maintain the values of the material. And then the last category is the third generation. In this case, this category is composed of food waste that is converted by microorganisms into biomass. So it's still an emerging technology, so we don't have many examples of this bioplastic, but they have a really good potential in the future for the low environmental impact. So we can say that the second and the third generation feedstock are the most preferred ones, alternative, because they are most aligned with the circular economy principles. Now, speaking about some numbers, we have the total global plastic production in 2023, that is 413 million tons. That is a really huge number and it's still growing. Speaking about Europe, in the 2023, we have produced 50 million tons of plastics. And worldwide, the amount of bioplastic produced in 2024 was 2 million. So the share of million tons. So the share of this quantity is around 1% or less. The same situation we have in Europe in the 2023, when the total amount we have the 33% of plastic that are recycled and only less than 1% that are bio-based. So which are the most common bioplastic worldwide? We have the 28% the epoxy resins, followed by the PLA and the PA. And then other materials with a less percentage. So now the question is how to assess the environmental performance of the material. The best methodology to use is the LCA, that means life cycle assessment. That is a systematic process to evaluate the performance of a material or a product throughout the whole life cycle. So starting from the raw material and ending with the end of life, the disposal of the material. So which is the objective is to identify which are the opportunities, the advantages, disadvantages of a material in terms of environmental performance. And also if we want to conduct a comparative LCA to compare it with, for example, for the bioplastic, a conventional plastics or other materials. Which are the phases of an LCA? First of all, we have to start with the goal and scope definition. In this phase, we have to define the functional unit, so what we want to measure, what we want to assess. Then to define the system boundaries, so what is included and what is excluded from the system, and to justify your choices. And then there are some reference flows, so the quantities of, for example, a material needed to satisfy the functional unit, the allocation rules that you use, and also really important, the benchmark material. So a material that has a functional equivalence with the one that you are assessing that you can compare with. And then the second phase is the life cycle inventories or LCI. Well, you have to map all the input and output of your process in terms of energy, materials, waste. In this case, you can use primary data that are data directly collected from the field or secondary data, so background data from database. The third phase is the life cycle impact assessment, where you can convert your LCE, so your numbers, into concrete results in terms of environmental results. And there are different methodology that you can use. The most recognized one is the EF 3.1, that is the most common in Europe. An example of indicator that you can calculate during this phase is the climate change. And then the last phase is the interpretation. That is really important because we have to identify which are the hotspots, so which are the performance of your material. And it's really important in the eco-design phase because you can suggest some adjustment or improvement for the. Which are the phases that you have to consider during an SCA? So when you perform an SCA, you can start from the resources, so the raw material. In the case of bio-based material, these are all the agricultural practices behind, so all the treatment of the land, of the crop. Then you can move to the processing phase, so all the processes regarding the polymerization of the biomass into the material, and so on. So with the consumption and the scraps, and all these parameters. Then there is the manufacturing. So when all the processes involved in transforming the bioplastic into your final product. Then there is the distribution. So you have to consider all the distribution from the field to the polymerization site or in the manufacturing site, and also the downstream transportation from the producer to the client. Then there is the use phase, so which are all the implications of the energy consumption, material usage during the use phase of the material. Like in our use case, we have considered zero. We haven't considered the space because we have zero consumption using the products. And then there is the end of life phase. That is one of the most important ones because depending on which treatment you have of your material, you have different environmental performances. So why assessing and conducting an LCA of a bio-based material is complex, and what we have to consider. So we have to consider, as I said, the raw material origin. So which kind of feedstock you are using for producing your bio-based material or bioplastic. Then you have to consider all the agricultural practices. So everything that happened during the agriculture of the crop. So which are the fertilizers, which are the transport, the treatment of the crop. And then you have to consider the land use change. So what I said previously, if a land was previously used for another crop and then converted into a land for producing bioplastics. Then other aspects are the energy source mix, so the type of energy used during the process, and this depends a lot depending on the region in which you are. So if you are in Spain or in Switzerland or in Italy. Then we have the polymerization process, which is the problem here. The problem is that when you produce a conventional plastic, the technologies are really efficient. In the case of new bio-based material, the technology are not really advanced, so there could be more consumption, more scrap, and they can have lower environmental performance due to this process. And then the last part is the end of life. So if the material is biodegradable, if not, it can be recycled or not. So all the evaluation on this. With our experience, we have mapped 4 key challenges that we have encountered during the SLA of a bio-based material. The first one is the limited inventory data. So in conventional database, it's difficult sometimes to find environmental data for this new bio-based material. So you are in a condition when you have to model the inventory from scratch. Then there is an high uncertainty in the process parameters. So as I said, for the polymerization of these materials, maybe you don't know all the processes or they are done at lab scale. So you have to consider for each case a particular parameter. And the data that are available sometimes are too general and difficult to model for to use for modeling a specific case. And then always, again, with the database, sometimes you can find a material on a database, but it's based on averages, so it's not specific for that material that we are assessing. And then at other times, there are some difficulties in the functional equivalence, so in finding a material that you can compare with yours due to different properties and characteristics of bio-based material compared to the conventional one. So due to all these challenges that we have identified, we have also created an internal methodology in SUPSI for assessing this kind of materials. The methodology is composed of 3 steps. The first step is to find a benchmark identification. So to find a fossil material that can have a functional equivalence. So the same performance, the same function in the products that can be applied in the same context. So for producing the same object. And then that has the same physical and chemical properties. And this is important because if you want to make a comparison, it has to be meaningful. So you have to compare the same material with the same properties. Then the second step is to find the data source to construct the LCD. So we have identified 2 scenarios. The first scenario, that is scenario A, is when you find a material on a database like a convent, and you just need to adjust some input and output to this process to characterize your specific material that you are modeling. And the second case, that is the one that we have used for SETCA, is to use a bottom-up approach. So you have to break down the material into subcomponents and to assess the impact of each subcomponent based on APDs, following the PEF guides, or based on a conventional literature. And then the final environmental assessment is the sum of all these inputs. And then at the end, we have the third phase, that is the comparison. So we have to pay attention on which is the methodology that you use, the methodology characterization that you use to assess this material. So it has to be the same also if you use different sources, data sources. And yes, and then you have to select the best benchmark for each indicator. So we shall the possible data, the possible LCE where you can find the data for your LCA. We have the APD, that are environmental product declaration, that are certified documents that you can that usually are provided by the producer of the material. So they are really specific and reliable because they are certified. So if you have these APDs available, it's the best way to proceed. So you have to choose this document. Then there are the PEP, that are some EU guidelines that help you in conducting the LCA. So what you have to consider, what you don't have to consider. Then there could be some literature sources. So you can search on literature and find some paper about a specific material. So you can identify, or you can use directly the impact if they use the same characterization method from the paper, or you can just take the input and output from the literature, from the paper, and reconstruct the material. So calculate your environmental performance. And then the last one, that is the most used one, is EconVent. It is a database where you can find some background process material. But the problem in this case is that it's not easy to find bioplastic in this database. They are usually not available, and data are usually generic. So you can use a generic PLA to model a specific PLA, like the one that we have used for SEP. Okay, so we move to the third phase of the LCA, so to analyze which are the impact for the bioplastics. So according to scientific literature, we have looked at some paper and we have built this slide with all the indicator. And what we know? We know that there are some indicators in which the bio-based material outperform the conventional plastic, and some indicators in which the bio-based bioplastic material perform worse than a fossil polymer. So for the one that are better, let's say, we have the climate change with a -35%, a fossil resource depletion with a -45%, a non-renewable energy use that is -35%, the carbon footprint that can be -55%, and also the water use. So what's the reason behind this reduction in the environmental emission? It is due to the use of biomass that comes from the corn plant respect to the oil. So we change this at the base, and also due to a particular characteristic of the crop, that is the carbon uptake. So during the growing of the crop, there is an absorption of CO2, and so you can compensate the emission during the polymerization of the phases. And then there are also some indicators that performs worse for the bio-based material. We have, for example, the eutrophication that performs from 5 to 12 times higher than conventional plastic. The land use from 50 to 250 times higher. The ozone depletion, the acidification, the ecotoxicity. So which are the reasons behind this worse performance of the materials? We have, for example, the use of fertilizers during the production of the crop, for the chemicals and additives that are used during the polymerization phase, was also during the production of the final material in order to guarantee the same characteristic with the conventional plastic. So, which is the key message to remember in this slide is that bio-based material is not automatically better than conventional plastic. So the best way to assess the material is that you have to use a multi-indicator LCA in order to consider different aspects. So not just considering the amount of CO2 that is produced, but also purification and use and so on. Another point that I want to stress on is the end-of-life scenario. So as the feedstock, this is another characteristic, another parameter that influences a lot the performance of the material. So depending on which is the end of life, you have different performances. In this slide, I have mapped 5 type of end of life scenario, starting from the best one to the worst one. So the best one is the mechanical recycling. The reason why it is the best one is because it preserves the material value and there are less GHG emission. So it's the most aligned with the circular economy principles. Then we have the industrial composting and the anaerobic digestions that are better than the landfill but worse than the mechanical recycling. The reason is that during the composting of the material, there are some emission of GHG, some emissions of methane, for example. And also because they are less aligned with the principle of circular economy because they don't preserve the value of the product at the end of the life. And then there is the incineration, that is a standard practice when you incinerate the product in order to recover energy. So which are the good aspects of this process is the recovery of the energy, but then you don't consider the value of the product itself because you burn it. And then there is the last one, that is the landfill. That is the worst one because when you leave these materials, like in a field, in a special place, in a special site, they produce methane that has global warming potential 20 times higher than CO2. So you eliminate the benefits that you gain with this material during the carbon uptakes. So if we want to summarize these 3 general issues, we have that there is the methane production during the composting and the landfill. Not all the bioplastics are recyclable, not all are biodegradable, and especially in conventional sites. And also you need the right condition for each kind of bioplastic. And then sometimes the suitable infrastructure are unavailable in that place. Or the volumes of these bioplastic are not enough big to build this kind of sites. So these are the main problems for these materials. Then if we want to move to AMBIANCE project, so to the second use case, in this project we have analyzed 3 pilots that everyone has developed a new kind of bioplastic or bio-based material. In this case, for SECTA, the comparison focusing on an existing scenario where there is a standard bench, outdoor bench, like the tempo bench in the photo on the left, that is composed by wood and steel, and then the new bench that was developed during the project with bio-based material, bioplastic, and using the large format additive manufacturing in AIMEN. So following the LCA methodology, first of all, if we want to perform a comparative analysis, we have to define the goal and scope of the assessment. So the first thing is the functional unit. For this case, we have identified as a functional unit 1 outdoor bench, providing seating for 4 persons. And as system boundaries, we have considered the cradle-to-cradle approach. So we consider the material starting from the raw material extraction to the end of life disposing. And the methodology is the EF 3.1. So after defining all these aspects, we have to move to the creation of an inventory. So we have to collect data, if it's possible, primary data from the pilot. Like in this case, for SECTA, we have collected data on the materials, so on the curtain steel and on the wood, on the manufacturing processes, so which are the sequence of processes to produce the final bench, which are the scraps, which are the energy consumption, the water use, and so on. And then we have also collected some information about which is the end of life of this bench and of the two material that compose the bench, like the steel. And then for the bio-based material, we have still collected information on the composition of the material, because it's a composite material of two different types of PLA, and with glass fiber to give it the best properties for printing. And for collecting this information, we have asked to the pilot, and then we have searched for this data source for the LCA analysis. And for the PLA mini, we have used an EPD that was provided by the producer. And for the other two, the information was collected from the AIMEN database. Then we have asked information about what was the process to produce the bench, and which is the scrap or the auxiliary materials needed for the final product. And then also we have collected some information about the recycling and the treatment of this bench at the end of life. What we have to consider during the LCA of 3D printing process is that basically we don't have on AIMEN database a process specific for 3D printing. So we have to collect some data from the cell. The first type of data that we need are the energy consumption. So we need all the consumption of all the equipments present in the cell for printing the final bench, like the speed, the energy consumption, and temperature. Then we need information about which is the scrap, because respect to a conventional material, for these new materials, there could be an higher scrap rate for the properties that it has. So it's important also to consider the amount of material that is scrapped. And then it's also important to consider what is the material composition, because if you add some additives or other materials, then the final performance of your material will be worse than a material just composed of PLA, for example. And this is now moving to the results. That is the third part of the LCA. For doing the assessment, we have used the Greta platform that Marco will explain later. And what are the results for the set use case? We have really good results, because 9 out of 11 indicators outperformed the conventional bench. So as I have explained before, we have some indicator that performs better, some indicator that performs worse. So we are aligned with the scientific literature. So which are the indicators that performs better? We have the climate change fossil and the climate change with a minus 69 and 59%. Then we have the material resources used, so that is minus 100%, and the water use. And the ones that perform worse are the eutrophication, ozone depletion, and climate change related to the land use. So all the results are aligned with what I have said before for the indicators. To sum up all these aspects, what we know about the bioplastic, we know that in some indicators they perform better, like the global warming change, in the climate change, and in some indicators they perform worse, like in the land use, eutrophication, and acidification. Another important point is it's what we have to consider in the LCA of this material, the feedstock. So if it's first, second, and third generation feedstock, and in the case that we want to help developer of this material, because this market is growing so fast in these last years, we have to help them doing the right choices and choosing which is the feedstock and other aspects. And then another important point to consider is that the end of life influences the performance of the material. Then to the LCA methodology, as I said, it's more complex to perform this kind of analysis for a new material. And the most important thing to consider is that you have to perform a multi-indicator analysis. So not just focus on one indicator, but consider more as environmental aspect, more environmental indicators. And also you have to pay attention to the data search and what to include and exclude in the analysis. And then finally for SECA, the final remark is that we have obtained good results in evaluation. So within the ambient project, a good job has been carried out. And now I will leave the floor to Marco.
Thank you, Valentina. The last part of the module, I would like to introduce our platform that is called Greta. Let me start to give you an overview why we decided to develop this platform in the last 5 years, basically. We want to solve basically two main problems. The first problem is from a sustainability expert. As Valentina explained us, it's quite complicated, especially today, perform right LCA analysis. And also, every time we have to adjust, develop different kind of approach methodology. So for this reason, we thought that basically sustainability experts need an instrument, a decision support system that help us basically to be more flexible as possible, adjust and develop also the methodology that we think is the best solution for the case. And usually LCA tool in the market, commercial market, are really strict and also are really focused on the basic analysis that we can perform in terms of LCA. The second point that we would like really to stress during the develop, we are under develop basically of this platform, is that we understood that use case, pilot, factory company, but also designer and engineering that develop material as in ambience, they really need something to help during this development phase, because of course they have the competence in terms of engineering and design. They know the product probably if a company, but as Valentina said, in terms of sustainability, sometimes it's difficult as an expert to explain possible problem, not because the focus is totally different. So with Greta, we would like also to allow let me say it this way, to allow the designer and engineering to perform some analysis, a preliminary analysis, and also perform some analysis in terms of interpretation of the result, and help them to bring a little bit the sustainability inside our and their basically normal daily operation. For this reason, we developed Greta. Greta, what is a platform basically, is a web application that we develop in different type of module, and we put all basically together. The main point, as I said, is have a single platform in order to not just perform LCA, but in some way, every time you use Greta, try to redesign and improve the performance of product on process. And to do this, basically, we focus in all 4 points that design and engineering and also sustainability expert need to stress during LCA phase, as Valentina explained us. So we focus a lot in terms of modeling in order to allow the sustainability expert to have more flexibility, as I said before, to gather data, to collect literature result, APDs, whatever, in order to build the model in quite easy way but also really precise. And in this model phase, we also try in the last year to implement some feature that we see before after this slide in order to have exactly the sustainability expert. Then the data gathering analysis, also in this way, we try to collect all the data with the traceability, let's say, but also in the best quality way. So if we have a machine that collects data, we can connect quite easy way, but also if we have APDs, we can collect directly the data from the database or the provider of the APD. Considering the optimization, the redesign phase, this part is more related to not sustainability expert. No? So in this case, instead of just show indicator that for a sustainability expert, it's quite a common way, let's say, to see the result, but for non-sustainability expert, it's not easy. In this way, we try to have a dashboard and also hotspot detection in order to help to play a little bit the designer and the engineering in different scenarios. We can compare different scenarios in real time and also with one model customize a little bit this scenario. And then finally, of course, the certification and reporting, because as you know, European Commission give us strict certification and reporting law, basically. So we also implement this space in order to be all aligned with what the European Commission asks. To go a little bit more in detail, as I said before, Greta is a platform. So we have two basically environmental. We call Greta Builder the part more for a sustainability expert, where we basically build the model and we can collect all different sources, methodologies on. And then we have what we call Greta Compass, which is more related to not sustainability experts, so the interpretation of the result, the optimization. So you can see under these two main environmental, we develop different type of project, specific functionality. In this case, for Ambience, we have the bio-based part that basically incorporates all the methodology that we develop and also highlight the different scenarios, the different indicators that we need to consider. But also, as you see, we can have different module now. We have optimization thanks to artificial intelligence, or now we have APDs, the code. So it's quite huge platform. To go a little bit more in detail, what I said before, Greta Builder is the modeling part. It's a simple, intuitive part because we think a dashboard in terms of visual modeling. So it's a drag and drop. You have everything on, let's say, on the path to model something product or process, and also the platform try to help you do this process in order to give all the possible warning if there is something that is missing, but also try to build, make it possible to build a model, not just to see one single product or process, but try to represent, let's say, more possible scenarios of this product and process. That's it's the basic that allowed us to make possible the design and the comparison scenario that we see in Greta Compass. Of course, in this case, for example, for Ambience, we developed a function that can integrate directly APDs. So instead of take the APDs from database and program operator, read, understand if the methodology is right or no, if the product can be compared with us, with our product, we can simply import all the database. The tool can check if everything is right. And so in terms of sustainability expert, it's quite something step forward now during the modeling phase. Then in Greta Compass, as I said, we see all the results. We see the result from dynamic scenario. What does it mean? It means that if we create a model that can be, for example, adjustment of material, process, supply chain, production machinery, whatever you want to play a little bit, it's possible. It's just one model switching one material, one scenario, depends, of course, the situation. And in real time, the Greta platform, especially Greta Compass, can give you the real-time assessment on the indicator. And also try to suggest you, if it's possible, possible improvement. So the platform can help you during the design phase. You can basically or chart or put some strict in terms of process, material, whatever, and the platform try, considering all the database that are inside, give you some advice in this direction, let's say. And of course, as you can see in the second picture, you can have different type of scenario and of the same product with different characteristics. This part is really important, especially for the eco design, I would say, but also for especially ambience, because we understood that during the design phase, who develop the technology or the material can really have a benefit to understand before to finalize the process if the direction can be in the right way or not. And the function of eco design incorporate a little bit all this feature. Of course, we, as I say, is a platform developed in different type of projects. So we, you can see also here some specific functionality in terms of APDs or PCR or fully traceability of the data. But basically, the main idea, as what is explained, give the concrete support to try to certify a new product or process, or better, or at least try to improve his product and process in terms of sustainability performance. The integration, Greta, as a web app, as I said before, and is a fully integrated. So what does it mean? We basically have integration in from output, so we can send the result of the LCA in different type of sources, can be just a label or a DPP or a PD, what it's needed. But more important is integrating the input. So if in the company or in the production facility or also in the laboratory that you develop the new material process, you have some ERP or just energy meter, we can collect data directly quite easy from them. So can avoid the problem, as Valentina explained us, that basically sometimes the data from database are not really the real data that we need. And when we play some indicator that can be worked in different scenarios, it's important to have the right data that basically can help in the most of the time improve the sustainability for performance instead of average data, let's say. Just a really quick video to show you what I said. Yeah, here you can see the modeling. So Greta Builder, you can drag and drop all the process and connect quite easy, and the model is build the product it's representing, let's say, and then in Greta Compass, as I said before, you can switch from one material and another, see all the result, and then compare multiple scenarios. So in the radar chart, in this case, we have all the indicator, but we can select, of course, and now is in the end of the demo, you can see that in the choose scenario, you can basically select all the alternatives that you want in real time in the radar chart. You can see the result. That's all from our side, I think.
Ένα γρήγορο μήνυμα να σου ευχαριστώ που είστε μαζί μας, που μας το ψάξατε, που...
There is one question online. So when you realize the LCA of the bio-based bench, did you use the PLA Lumini emission factor that consider the biogenic carbon embedded in the product? If not, why not?
No, we are using it because we have to.
Please, the microphone.
Yes, we have to consider also that indicator because we have to consider the special part of the benefit of a bioplastic, that is the carbon uptake. So it's important to consider that indicator.
Okay, any questions?
At the beginning, I thought that it was on the analysis of the input conditions from the bench, preparing the bench. It was around 300 kilograms scrap. And I wanted to know if this was referring to the actual weight of the whole bench when it is scrap at the end of life, or it was scrap.
No, it's a mistake, sorry. It's not 300 kilo scraps. So it's the amount of material that is used for producing the bench. No.
Makes sense. Okay. Thank you.
Sorry.
So yeah, very interesting results, and also very interesting the result that came out of the RCA. It's really impressive. But I have one question here, because have you taken into account the life of the bench? So for instance, they made from wood of steel maybe it's 10 years or so, while for the biobase it's maybe 2 years. But on the other hand, with the bioplastic one, with the bench made of bioplastic, it could be reused. So it would give a second life to the material. Has been those two things taken into account in the analysis?
We have considered all these aspects, not in this assessment that I have shown, but we have modeled considering different life cycle of the bench. So 3 life cycles. The first one that is produced with the virgin material, and then the end of life recycled. Then the second one with the material input that is recycled, and then the end of life recycled. And the last one for the new solution that is the material recycled and the end of life disposed. So we have in Greta, we have 3 different, let's say, environment where we can decide if we want to compare one life cycle of the conventional one and the new solution, or 3 life cycle, and see if there are improvements in considering more life cycles.
That's basically allow you to compare the same lifetime, because if we perform in this way in order to, as I said, if you have the lifetime of the benchmark 4 year, let's make it 6 year, and we know that our product is 2 years. In the first case, with the one life cycle, you can compare just the product. But if you go for a 3 life cycle, so every time you recycle, the advantage can be better. So you can compare basically. We compare basically also in terms of lifetime. So of course, the biobase will be 3 times because the duration can be 2 and 2. The baseline is just 1 for 6 years, but yeah, we perform exactly in this way in order to highlight. Okay, we have to remake probably, but we can retake exactly the same material and so on. So the performance, the environmental performance can be also from long term and not just the production and so on.
Still the results are as good.
Yes, not in this way, but we have to think that the recycling that we have modeled is a sort of internal recycling. So when you produce in the first cycle a bench, then you recycle that material for producing another bench, and that doesn't happen for the traditional bench. So the quantity of material involved in the second cycle is not 300 kilos, but is less because there is a recycled chemical. So we can say that they are quite similar to.
Of course, in terms of percentage, the best advantage you can have, as you see in the first one. But we demonstrate, let's say that considering all the lifetime, we have instead an advantage in the end. Of course, in terms of number is a little bit lower, but yeah.
Very interesting.
Yeah.
This question is not only for printed bio-based plastic, but bioplastics in general, bio-based plastics. Because I'm always curious, what is the comparison about the environmental impact between non-bio-based thermoplastics like PETG and bio-based new plastic? The difference is that the non-bio-based are, like I'm referring about non-bio-based recycled or already recycled compared to new bio-based plastic. considering that at the end of life, both are thermoplastic and recyclable. Because it is always this question, what is better? Something that you need to create from new, like bio-based solution, or something that is not bio-based, but it was already there and has been recycled, and it's already possible to recycle sometime after.
So the best solution is recycling for sure. So not creating something from new, because you keep the value of the product. That's it, simple. So if the question is if it's better a bioplastic with a recycled material, maybe for some indicators, a recycled material is better. A bioplastic that is created from virgins, but it depends on the bio-based material.
Also, you take into account that the non-bio-based is not biodisposable, like for example the PLA. It's also that taken into account in this balance that recycle is always better, but I don't know if it has a big weight, the fact that even though it is non-bio-based and it is recycled, it is not as biodegradable like PLAs, for example.
The point is that, of course, in general terms, as Valentina said, it could be better recycled. But I totally agree with you that sometimes it's not the case. For this reason, that we also play a lot in order to allow the user to compare this scenario, because we saw in the last year in different cases that there isn't really a path that every time is better to do one thing, because also considering the recycle phase is something really complex, because depend of the material, if we know the supply chain or not. So the difference between the two scenarios can be really something important to consider. So the best way would be, in my opinion, try to compare instantly or in real time, or in not 2 years, but in a couple of weeks, different type of scenario, considering the data that we have. Also, average data from database can be 80%, let's say, reasonable for comparison, and understand in the case which the best solution.
Could be this type of comparison be assessed on Greta?
Yeah. We basically understood in the last couple of years that the main point is allow the comparison during the developer phase. So of course the final result will be in the second phase when we have all the data. But if, for example, in Ambience, from month 1, we decide to develop these 3 types of material, we can compare possible scenario in terms of, okay, this material is recycled, but we don't have the supply chain, or this is composable and whatever. For sure, can help you to understand which best solution before to develop all the field. So we try to stress a lot about this function. It's something really for the case, of course, because also the to with the developer is something depend of if you can, because in this case, in some case, you cannot totally change the material in terms of performance. So, but in some case, it's the case. We develop, for example, a material from wood that we discover that in theory the wood is better of plastic, But we understood that for the performance of the product, we have to add just a small quantity of additive that is destroy everything in terms of environmental performance.
I guess also the type of wood is considered, right?
Exactly.
So not some of them are so good for them.
Exactly. So in the first phase of the developer for the product, we compare like 10 scenarios, quite easy way to say. And the company understood that probably the idea was not so clever in terms of environmental performance. So yeah.
Is Pirotta available to the public? It's going to be commercialized?
The idea will be commercialized like a spin-off for the university. Now we are developed like more the graphical interface because of course in the last year was more for internal use or project use. So we are stressing the last couple of months, but the idea will be develop some spin-off from SUPSI and use also from commercial. Yeah.
It would be very useful.
We gather a lot of interest, especially in this field. So yeah, they are discussed with our university.
Thank you.
Thank you.
Short intro again. Why is smart testing important for a greener future? It's because if we can detect the defects early, we can avoid to produce defect parts. So it helps us to manage our resource efficiency and reduce our waste. The second point is that if we understand the material with non-destructive testing, we can extend the component lifetime. And the third point is if we make real-time measurements during the production or the process, we can more efficiency with our energy and the processes of the production lines. So overall, smart testing can help us to reduce resources, energy consumption, and helps us to avoid environmental impact. And this is why non-destructive testing is essential for smart testing. Because, so what is non-destructive testing? Non-destructive testing means that we can inspect, characterize, and evaluate materials, products without damaging them. This helps and also gives us information about the products of the structural, chemical, and functional behavior of the product. And in combination with this, it enables us to make inline and outline control, quality control, or process controls. So bio-based materials, Valentina gave us a good overlook about bio-based materials, so I can make it short. Many bio-based materials have their challenges in their structure, about how they build up with fibers, fine, different fillers, combinations, and they are sensitive to moisture, to the uptake. And this also allows them or makes them a lower durability or has an impact on their lifetime and also on their mechanical properties and limitations of the bio-based materials. They are sometimes not easy to produce, and also the processing is challenging of the materials. And also sometimes some materials are easy to recycle, some of the bio-based materials are not easy to recycle because of the combination of fiber, fossil-based, bio-based combination, and also of the end of lifetime. This is where NDT can help to contribute. We can easily detect moisture with many kinds of detectors, not only on the surface, also directly through the whole sample. We can analyze with non-destructive testing methods the structural combinations, the fiber orientation, and give an information about the mechanical properties, their strength, and all. One important thing is to avoid defects. We can directly, with NDT methods, directly detect defects, the lamination or breaks in the samples during the production line, and so reduce the waste. And also for the long time monitoring, to monitor the aging of bio-based or in general materials is really important to have an input how long we can use it, when we should recycle it or change it. And also big point is also the quality control directly in the process or production line. So which methods can we use? There are many methods in NDT. We have the acoustic method, which means just like acoustic emission or ultrasonic, if everybody knows from the hospitals. We have optic methods, just like OCT or stick with this digital imaging correlation. There are the many standard methods of radiographic, just X-ray or the CT. And also we have also the electromagnetic methods, just the microwave methods. Everyone knows the thermal with the infrared camera, thermographic methods. And there are many spectroscopic methods, just terahertz, infrared methods to use for the use in NDT. Recent, we have concentrated of non-contact, and this means we're using acoustic and optics. And we use it. Is there a question? Well, okay.
Yes.
We have the acoustic parts where we use laser ultrasonic and photoacoustic. And we have optic methods where we have terahertz, optical coherence tomography, infrared and Raman spectroscopy, the thermography, and also the quantum sensing. And today in my talk, I will concentrate on 4 of these methods, which are more suitable for the bio-based materials, and where I have some examples to show for you what we can do with non-destructive testing. At first, I will start with laser ultrasonic, which is a contactless ultrasound method where we use laser for exciting and also for detecting the ultrasonic signal. It is based on pulse echo scanning, where we can make images, fast images in B and C scans. And during the contactless behavior of this method, you can investigate it at hazardous or dangerous places and really hot and cold materials, and also very sensitive materials. With laser ultrasonic, we can measure the layer thickness, also the delamination, and the defect detection in many samples. And here I have an example for using laser ultrasonic in a quality inspection for carbon fiber composites. I have here. When it's well, normally in this video you can see images. It's wander through the samples, and you can see the delamination of this carbon fiber plates. We were scanning in fast time over the sample and making a 2D image and going through the C scans. Images. And also, this was working. Yeah. Another big advantage is you can put it on a robotic arm and scanning over big samples and find delaminations or cracks in the samples. Now we come to the next method. This is optical coherence tomography, or so-called OCT. It's also one of the contactless and non-destructive testing methods which we use in RECENT. It is an interferometric method where laser is used to imaging in subsurfaces of ceramics, bio-based materials, biological tissues. It's a really high resolution. We can have occurrence down to sub-micrometers. And we can fast imaging with short measurements periods of several cross sections and per second. And also in special cases, we can make also spectroscopic imaging with OCT. Here we have also an example for quality inspection of a polymer UD tape where glass fibers is embedded during a matrix. And we want to scan during the whole production process at a special place to find out if the glass fibers are bundled or flat over the whole tape, and give back some input to the machine to slower, faster, it's too bubbling. Yeah. And we can make have a rough surface or have a smooth surface if they're over all glass fibers. Matrix. Another example was a direct in situ detection of the flow instability of an extruder, where we have one fluid down was a special adhesive, and the fluid up was a HDPE. And we want to inspect and give also parameters to the extruder, how to make change the pressure or change the speed, faster, slower. But OCT has high resolution but a limited penetration depth, so we came up to terahertz, which have the advantage that it has a higher penetration depth and resolution up from millimeters to submillimeters. It's also terahertz is in the range between microwaves and the infrared range, and is also interferometric method where we can scan through the pulses, and also we can use it for making not only spectroscopic measurements, also making to find out layer thickness, delaminations, or in our case, moisture detections also. And we also can make 3D computer tomography with terahertz. Here I have an example to how we can detect the layer thickness with the terahertz signal. We use the time signal where we have the front layer, the next terahertz pulse, the refraction come back from the second layer, then is there a little air gap between. In this case, could be also detecting some delaminations, and then the last layer. And in this case, we have a multi-layer, so we can imaging the different layers. But if we have only one single layer, we can also get the spectroscopic information, the chemical fingerprint of the polymer or of other chemicals inside. This is our fast imaging CT. If it works, no. In some reasons, it's very important to have around the samples to get more information from the sample, especially you have something inside the tube or want to know about, I don't want cutting the polymer tube or the layer. So a CT can be very advantage. Another advantage of terahertz is the hyperspectral imaging, where you can use during the production to find out if you the right combination of polymers, chemicals inside, also to find something that you don't want. If in the recycling plant you don't want in your recycled material, if there's something in it that you don't want for recycling. And also afterwards I will show a small demo with this moisture detection sensor, which are developed in the AMBIANCE project for detecting moisture in the panels, which are also sit outside. And therefore we use a sub-terahertz source to eliminate the samples. Can be all kind of bio-based samples if you calibrate the sensor for them. And the reflected signal we get will sum up over the 2D image and make the mean, and we can calculate back to the moisture in the sample. Another important method in RECENT is the infrared spectroscopy. It's you get the main information from the vibrations of the molecules in the samples, and you can use it for all kind of solid, liquid, and gas. But you have a lower penetration depth, so mainly you get the information from the surface. But also that information can be important for all of us. Here I have an example of the inline chemical process monitoring of high pressure laminates, where we have a small NER spectrometer, which is implemented direct in the production line and making a real-time monitoring of the resin curing process of the high pressure laminates and gives back feedback to the system about the drying, the curing, and making a stable NER spectra for them. Also during the movement of the conveyor belt. And down you can see the curing spectra over the wavelength and the change of the curing degree. And this is the reason why I use it as a complementary method in the AMBIANCE project for detecting moisture. You can use this small detector for detect moisture with the 2 bandwidth absorption bands of water. And here we have an example of a drying process direct in the production line of, I think it's what of food, it was small pieces of bread. And also to give feedback to the system to heat up, drying more. And yeah, it increased the energy efficiency and also reduces the CO2 footprint of the production line by using that more efficient, with more intensive of the sensor data. And also it's also important point it is a low cost sensor. It's more interested for the industry. But to have a really good NDT method, every method has its limits. So if you combine these methods, just like we do it here with all of OCT, infrared, terahertz, and in combination with the tensile test stage, you can get out for the best thing of all of these methods. And get more information, not only from one method, in this case of 4 methods. So in short, to sum up why NDT is a broad field of many things you can see, characterize, evaluation, imaging of the whole thing, and also make a process optimization, getting into processes in combination with machine learning. You can optimize the processes definitely better and get more information. But it's not always easy to have the right method. You have to choose which is the right method. It depends on the material. It depends, do you need high resolution and a low penetration depth, or do you need good resolution, but especially some points of these methods are, some of these methods just like X-ray have ionized radiation, which is not healthy. And other methods, just like ultrasonically, are not conductless. You can use it everywhere. You need a couple media for ultrasonic. Okay. You have to choose the right frequency range and also find a way to connect it with machine learning, data learning, to make a big amount of measurements. And for NDT, the outlook is if we get more, there's many things they are doing in the making sensors. They are getting smaller, embedded directly in something. We can use conductive polymer layers to make smaller sensors. And then you can easily use it everywhere. And if we combine all of the most for us important methods, NDT methods, we can get more information. And that's in combination with robotic, you can be flexible. A big point nowadays in coming up is the data analysis in combination with artificial intelligence and machine learning. But we don't have to forget that the machine learns from us and artificial intelligence. So we have, there must also be somewhere to control. And this is will be a long process to get artificial intelligence and not so long process, but we in the companies, because you need to collect data, control the data, supervise the artificial intelligence, and it will be a lot of work to implement if it runs smoothly, that it runs smoothly in the production. So now I will show you a short demonstration down there. I'm sorry for the Teams people, you can see it. Don't think so.
Does it see the speaker?
But you also can stand up and come outside to wake up.
This is not. Yeah, this is quite easy.
For AMBIANCE, we designed a small terahertz sensor to detect moisture directly in the outer field on the panels, which they are outside there, or we see it tomorrow.
Just because we are switching the camera for the people and able to see.
The sharing of the sweets we have someone yes. Can you see it?
Yes.
Okay. Now we see. Okay. Yeah. We have here this terahertz sensor where we put a sample. We need some reflective foil behind them. It's not perfect because there's some air between. Yeah. But you can see the reflection and you can see my finger. It's highly absorbing water.
Want to speak a bit louder?
Okay. Does it work better? Yeah. And the terahertz source is here and eliminate the sample. And now it's dry, so we don't have any, it's in the reflection, but we don't have any absorption in the measure. And if we put, this is not a little bit too extreme. If we get water on the sample, you can see the terahertz signal is absorbed and reduces awesome. That means higher water content in some samples means lower terahertz signal coming back. And I also have this small complementary NES sensor from our infrared group. Dry sample. And can see here the spectra where the difference is between the two wavelengths, which are measured. Now we have really small difference. And if I go to a wet sample, we have higher absorption of the wavelength. And we also can monitor the drying process during, I'm holding the sensor on the wet sample because there's light and they will dry the samples over time. Sometimes. Yeah. And if I do it. Thank you to both of from myself. And if you have any questions or want to test it, as possibility.
We can go back to ask question, I guess.
Can close this now?
Do you have any questions?
One question. Regarding the technique, the characteristics you indicated that it has a higher penetration than, for example, the near infrared. But do you have the possibility to determine profiles of, for example, humidity in the thickness or?
Yes. No, not at the moment with this.
Cannot stay there.
Okay. With this, we don't have to profile it in the depth. Therefore, we have to use the other system, the spectroscopic. This is a CV, terahertz CV new system, and the other from Toptica is a time domain system where we can resolve over the whole time signal which coming back. So it could be possible to have that information. Almost.
Do we still have time for more questions?
We have time, yes.
Okay. And regarding the laser stuff, can it be used for those product or parts with complicated geometries?
Yeah.
Because I think that from all the NDT method, you show that this one, the laser one, is one of the few, or if not one of the only one, is that it can be used for kind of conductive material.
Yes, but also OCT can be.
OCT, yeah, okay. But
on the surface, not directly in the. It depends what you want to see. If you want to see through the sample, for conductive materials, is laser ultrasonic. If you want to see the surface or a little bit the first layer, also the other methods can be used. Also terahertz can be used.
Yeah, but for the loose, that one, it can see both on the surface and go through the thickness.
Yeah.
And also for parts with complicated geometries.
Yeah.
But will there be any risk from the laser beam? Because you are going to apply any laser.
Yeah, there could be risk. It depends on the power you need for the samples, and also it's a pulse laser and the wavelength. But yeah, you can put it in. Also, just like the radiographic systems, the CT system, you can put it in a box, and you don't need a box with metal in it. So you only need a box to provide to the laser beams, the scattering come out.
But we can control the risk if there's any.
Yeah, you can control the risk.
Final question. For now, the terahertz, you have said it has, I also know it before, chemical fingerprint.
Yeah.
Can it be used for instance, during the manufacturing, detect the curing degree?
Yeah, can be used.
Thank you.
If there is time, I have another question. So maybe it's a general question, and based on your experience, because here at AIMEN we are facing a project in which we are fabricating a heat exchanger made of ceramic, made of alumina, is for air. Yeah. So we have very complex shape, and an issue that we want to solve is is for an air heat exchanger. So we have to prevent leakages and defects within the structure. So based on your experience, what do you think that would be the best way to evaluate this?
It's ceramic and aluminium.
It's alumina. Alumina is a ceramic.
Therefore, we have that wasn't in this presentation, we have experience with small grids in with MER OCT, which was developed in our company. I can show you later some.
Yeah. Please, if you can send me.
If it's OCT for small, and if you have bigger parts, you can use a thermographic. Also, we have also the laser ultrasonic with.
But it will be possible to detect very small defects because the defects that I'm talking about, I mean, those parts will be made by 3D printing. So it's just.
Do you mean Economics 3D printing?
Yes.
Okay, yeah, we can talk that, MER,
Okay.
OCT, maybe in combination with our new fund sampling, which making faster, smaller results.
Okay.
Yeah.
Yeah, it'd be nice to know more about it.
We are a bit early on the schedule, but we can move on to the next and final module.
It's already here in the presentation.
Yes. There's your presentation.
El módulo 4.
System. So please check if
Now it's the folder.
it's the folder.
Yes.
So I will try to open again from the folder and see if it works. It's the folder.
Still the folder. Yes. Try to stop the video sharing. Do you have the presentation open? Yes. No.
No. Yes.
I see if now you can share the page. No, before it was Raquel, now the.
Yeah. She's not here, so yeah.
No, try on Teams. It's on Edge. You have to go on, if you haven't used the, yeah. Up. No, up. Giulio, guarda se legge con il. Should you like me to keep please?
No os aparece el PowerPoint porque lo tenéis minimizado. Abre el PowerPoint.
Pues
Vale, y ahora clic. No.
No, ok.
Y ahora, ahí estás.
Grazie.
So now are you seeing the? Okay. So yeah, let's start with the last module of the training. It's from biopolymers to alternative cements, evaluating sustainability materials for additive manufacturing. So for this module, we have it split in 3 presentations. I will be doing the first one, which is about the transition or what we need to do in thermoplastic materials for transitioning from small scale to large scale. Then my colleague Xabier will speak about the actual application in large format with thermoplastics. And finally, Miguel will speak about the work that we are doing here at AIMEN in developing a new bio-based cements and also cements with low carbon footprint and also its printability and its printing in large format applications. But let's start with the adequation of thermoplastic materials for the large format 3D printing. So of course, this is not a trivial step. So whenever we are moving from small scale to large scale, there are there are quite a lot of factors that you need to be aware of. But there are three that are probably the most crucial. And we have always to have them in mind. So first is the thermal shrinkage and the warping. And this is mostly related with the temperature control. So usually in large format 3D printing, the control of the temperature is poorer than what we have in the small scale. This is of course for obvious reason. The time between layers is of course much longer because the parts are also larger. And also the building chamber is much larger. So again, the control, all those things make the control of the temperature more critical. So what happens here is that, of course, when the material cools, there is a thermal contraction effect that in those large parts, whenever there are variations of the temperature, occurs unevenly. And this, of course, causes warping, which is probably one of the major issues that we face whenever we are working in large format. For that reason, all materials for large format 3D printing require the addition of fillers to reduce this thermal contraction. So that's the first effect to be aware of. The second is the crystallization and weldability. And this is very much related to the time between layers. In those large parts, the time between layers is much longer than in the small scale 3D printing. For that reason, often the temperature in the layer that you have deposited is much lower than in a small scale 3D printing. So meaning that when you are applying the second layer, the ability of the polymer change to move in the interface that's reduced. And this affects a lot the weldability and of course the thermal addition, which in last term affect the quality of the part that you are fabricating. And the third factor to be aware of is the thermal instability, which is very much related to the residence time. In large format or in large scale 3D printing, the time that the material is within the extruder is much longer than in a small scale 3D printer. For that reason, the material is submitted for longer to high shear and high temperatures. So it has very strict requirements in terms of thermal resistance and also resistance to the shear forces. So all those three things are something that we have to be aware of and consider whenever we are doing fabrication at a large scale. So I will skip this slide because it's just to put in a fancy way the many benefits of using 3D printing compared with other manufacturing techniques. But let's focus on what we have done with the material for the AMBIANCE project. So here in the slide, I'm showing some of the general requirements that we established at the very beginning of the project for the material to be used in AMBIANCE for the fabrication of the urban furniture element. So of course there is a cost factor, so the material should have a reasonable cost. The material should be as well bio-based, should be available in large quantities, and it's mandatory that the material could be processable in large format fabrication, and also it should have enough mechanical properties, adequate mechanical properties, and also optimal resistance against UV and humidity, because those are elements that are going to be exposed outdoors. So once we knew all those requirements, we start to look for appropriate materials for the AMBIANCE, and we decided to focus on PLA. Why PLA? Because the cost is reasonable. There are many producers of PLA. There are many different degrees of PLA available in the market. And also, we know for sure that it's a material that is simple to process whenever it comes to 3D printing. So once we decide to go for PLA, we start to look for the most appropriate materials, and we select 4. I just call them A, B, C, and D because this is not a commercial talk. I don't want to make any publicity. So just let's call them A, B, C, and D. A is a traditional PLA. It's an amorphous PLA that we know for sure that this material will never fulfill the durability requirements of ambience, but it's a material that we know that can be printed in large format, and we would use it as a baseline, as a reference to evaluate, to assess the printability of the other three materials. Then B, C, and D, they are special PLAs. They are commercialized as QB and humidity resistant PLAs, so they are potential candidates for the ambience project. All four materials, A, B, C, and D, they are commercialized as materials for 3D printing, for small scale 3D printing. So the first thing we did is to apply a protocol that we have developed here internally at AIMEN, based on parallel plate rheology. And by this way, we assess the potential of the material for doing the transition from the small scale to the large scale 3D printing. We evaluate three main parameters. First is the compressed viscosity. The compressed viscosity gives us very interesting information regarding the flowability and the shape stability of the material. Flowability is how is the material flow through the nozzle, and shape stability is the ability of the material to retain the shape when it exits the nozzle. Both are critical parameters in 3D fabrication. Then with the viscoelastic characteristics of the material, so the G prime and G second, so the storage and elastic modulus, and the ratio between them, we evaluate how is the viscoelastic behavior, how is the material, and also how is this material dissipate stresses. And this gives us a lot of information regarding the propensity of the material to suffer warping. And finally, we analyze the relaxation modulus. This is a derived parameter, but by using the so-called Dalwich criterion, which is very well reported in literature, we can analyze very well the potential of the material to get to provide a good addition and a good part quality. So to do the assessment, basically what we have done is the following. For the reference material A, we gave a score of 0, and then for the other materials, depending whether the performance is better or poorer than the reference material, we give a positive or a negative score. And this is what we have obtained, so what I'm showing you in the table. Of course, for material A, we have a score of 0, and for B, C, and D, we get, in all cases, negative scores, meaning that those materials are going to be more difficult to print in the large format than the reference material, the material A. But if you look at the C and D, the values we got are far more negative than the case of B, meaning that those are the most difficult materials to print. And somehow B is in the middle, in between C and D. So from a manufacturing point of view, our preferred choice is material B. Something important that I should mention here is that among all those characteristics that I'm showing in the table, so flowability, shape stability, warping, and interlayer addition, the flowability, the shape stability, and interlayer addition depends mostly on the material. So this is not something that you can modify easily with the processing conditions. It depends on the material. So you should have a clear picture of those parameters in the material to know their potential for 3D printing. In the case of warping, the situation is slightly different. Of course, warping depends a lot on the nature of the material, but this is something that you can play with just modifying the fabrication conditions. So, once we select material B for going to the large scale, next thing was to do actual fabrication trials in the large format fabrication cell that we have here at AIMEN. And as we could foresee from the rheological analysis, we observed warping and delamination. So what are the causes of warping? There are two main reasons. One is more physical and the other one is more physical-chemical. So the first reason is the thermal contraction, that all materials expand whenever they cool. And this is something that we had somehow controlled by adding fillers. By adding fillers, we are able to lower the contraction that the material is suffering. But there is another factor playing in the warping, and it's the ability of the material to relax stresses, and it's related to the viscoelastic nature of the material. And this is not something that we can easily change by adding fillers. We need to modify the chemical composition of the material. How we do it in ambience? Basically, here we blend the original material B with another material with a more amorphous nature, so increasing the viscous character of the blend. So we did, of course, many different trials, adding different amounts of fillers and different fractions of the amorphous material until we got the sweet formulation, the one that we could print in the large format without suffering warping. Of course, in parallel, this work on the material, there was work on optimization, the fabrication conditions, until we found, as I mentioned before, the sweet point, where we have a good material and we have optimized fabrication conditions. And how a good material looks like is what I'm trying to show you here in this slide. So if you look to the picture on the top, the right top, so it's the complex viscosity curve. So as you see, the curve follow a very nice trend. So we have a high frequencies, low viscosity. Then when the viscosity is increasing, when the frequency is increasing, the viscosity goes higher. This is the so-called shear thinning effect, and this is precisely what we look for in 3D printing. At the high frequencies, we are mimicking what's happening inside the extruder. So we need low viscosity for the material to flow. When we are going to low frequencies, is what happens when the material exits the nozzle. And here we request high viscosities for the material able to maintain the shape. Of course, this viscosity at the exit of the nozzle should not be too high, because otherwise we could have issues with the plugging, and this is not ideal, of course. But what we got with this material is very nice. We are within the limits of viscosity, and we are getting this nice shear thinning effect. Next, if we go to the bottom left, is the curve where we are showing the two modules, the G prime and G second, so the elastic and the storage modulus. As you could see here, I don't know if you can see well in the presentation, I hope it's big enough, but in the whole range of frequencies, the storage modulus is over the elastic modulus. This indicates a viscous nature of the material, which is very good for dissipating stresses, for preventing warping, and also helps the interlayer adhesion. And if you look to the graph in the middle, in the bottom middle, is a better way to illustrate this viscous nature of the polymer, of the material. This is the time delta curve, where they're plotting the ratio between the storage and the elastic modulus. And what's important here is to look at the low frequency ranges. And here in the low frequency ranges, the red curve is the original material B, while the black curve is the compounded material, the one that we have modified with fillers and with another amorphous fraction. We see here that the values of tan delta is in the range of 3 to 4, which is ideal for energy dissipation and preventing the accumulation of stresses on the part, and also the warping. And finally, on the right is the relaxation modulus curve. So we see here that the curve fits perfectly within the darkest region. This anticipates also a good interlayer adhesion, so a good quality part. Of course, once the material was prepared, we give it to our colleagues that do the actual fabrication for making the manufacturing of the urban furniture elements that we have fabricated in AMBIANCE. But besides this adequation of the material for 3D printing, another relevant issue here is to assure that the material is able to withstand outdoor conditions, so resistance to humidity and UV radiation. And we have verified this in two different ways. So with laboratory tests using a climatic test chamber, and also in real exposure tests that they started 3 years ago in May 2023 and just finished a few weeks ago. So 3 years exposure. I have no time now to enter in detail. I will give the floor to my colleague Xabier to discuss about the fabrication of the elements in AMBIANCE, but what I could tell you is that the material that was compounded here at AIMEN passed the durability test successfully. And that's all from my side. So Xabier, the floor is yours.
Yeah.
Okay, so I will focus on the manufacturing processes of the bio-based thermographic developed in Ambiance, plus some other developments and technology and software developments we have in AIMEN that are closely related to the Ambiance project. So first, I would like to start with a brief introduction on additive manufacturing processes for thermoplastics. So traditionally, we know the filament-based additive manufacturing process, which is a schematic on the left side. This is a very homogeneous and precise flow of rate control that usually produces very high quality parts. You can have the ability to retract the filament so that the position control is very good. And it's a very available technology. It's very well known. It's around 10, 12 years now since it was started to be very popular. And nowadays it's a quite economical technology. On the other side, we have the fused granulate fabrication. It's not so common. It's more focused on high deposition rates to create very large parts. The feedstock, instead of the filament, is kind of a chopped filament in the shape of pellets, like lentils, small balls, small cylinders. It's more economical generally. It's more sustainable and recyclable because the feedstock, it does not need the filamentation process, which is quite complex due to the very high tolerances that the filaments need to have to be well processable by filament extrusion based. And also a very important fact about pellet-based deposition is that you have the ability to include higher fiber content. Whereas on the filament, you have a content in fiber around 10-15%. On pellet deposition, you can have from 20 to up to 40% fiber content. So this will make much more stiffer parts. Then on the most unique systems, you have the usual Cartesian 3D printers that are usually through motion accesses, and you tend to print in parallel planes to the base. They are experimental machines that overcome this limitation, but they are not on the market. You have the open 3D printers that are for processing PLAs, PETGs, polymers that are commodity polymers, don't need high temperature chambers. The one on the right, the 3D black printer that we can see there, is a high temperature printer that is more focused on engineering grade polymers. And the difference is that you can set the chamber temperature just like an oven. So you have a temperature close to the TG of the polymer during all the process. And you can have addition and prevent warping and thermal gradients during the process. On the robotic 3D printing, it's more industrial 3D printing. You have 6+ motion accesses, like you can see on this image. There are 6 motion accesses on the robot and 1 external on the track that is moving the sideways the robot. On this scenario, the printing is not only limited to planes. You can do non-planar 3D printing and also the variable layer height, meaning that you can have layer heights that, for example, on the external, if you were able to print a curve of pipe, on the external radius will be a higher layer height than on the interior curve of the pipe radius. Then, since these two motion platforms are quite different on the position strategies, I would like to remember the design strategies that you need to apply to convert a standard part on a part that is manufactured by additive manufacturing. This applies, these ones that we can see here, they apply for filament 3D printing and pellet-based 3D printing, robotic Cartesian printers. They are the basics ones. So we can see that the wall thickness, you should tailor the wall of the part to the bed thickness that is producing the nozzle. You should take care of the overhang angles and the sailings and type of integrated supports, meaning that you adapt the geometry so you don't have a need for support material because you are playing always against the gravity unless you are printing non-planarly, as we will see later. Also, you should apply rounding strategies like fillets for the corners, and so you adapt them to the diameter of the nozzle. Chamfers is also a strategy of overcoming the overhangs, and also you should look carefully for the part orientation to minimize the amount of supports or overhangs that your part will need. Okay, so we can see now a bit more in detail these constraints regarding the technology. So the main drivers of these constraints are that on filament, you can't stop the flow. It's very easily, you just pull up the filament and the polymer will not keep pouring through the nozzle. But on pellet extrusion, the molten material is inside a big cylinder. There's nothing to prevent it from oozing out the nozzle. So it will, if you are not printing and you lift up the extruder head, it will pour through the nozzle. So in this situation, you should avoid making travels and discontinuities between the walls, aiming to design for continuous trajectories. So you should integrate, for example, the infill into the design, and you should avoid unsupported periods because this is another key difference with filament extrusion, that you don't have here the possibility to use support material. So there are other strategies to not use support and successfully print features like ceilings. So we can see here some of the main methodologies when you are printing on large format with pellet extrusion heads. You can design solid and then you print only the perimeters, which usually is known as the base mold. On this first image to the left, you would lie the part down on one of its sides and beat it vertically. This was from a project that was about making also furniture, but for indoors, also with bio-based materials. So it's kind of the precursors of ambience. On the central one, you can see how the infill structure is integrated into the design. You would be able to vary the thickness and have more beads in the walls if it is necessary to be more reinforced. And on the side is one design strategy that is not based on solid models, but on surfaces without thickness. So this surface, which actually do, is to guide the nozzle.
Hello everyone, my name is Miguel Otero. I work as a researcher in AIMEN in the same group as Ricardo and Xabier, the Composite Technology Department. But my research line is a little different. It's about 3D printing of cement materials. In our case, compared to the 3D printing of polymers, we do not apply heat. In our case, to control the gravity is crucial, so we need a fresh concrete that can be extruded smoothly through the nozzle. This property is called extrudability. At the same time, our material must contain its shape after deposition and to support the weight of the upper layer. So this property is called buildability. So we need a balance between extrudability and buildability. And at the same time, cementitious materials are reactive. So we need to control the open time because hydration reactions occur just after mixing. So this makes it a little bit difficult compared to polymer. In my opinion, from a material point of view, it's harder. And during my presentation, I will also talk about bio-based material, which different bio-based material can be incorporated into concrete materials. Especially, I will focus in the Biogens project that I'm an architect of. I'm also pursuing a PhD in the framework of this project, and I will show some of my results. So I will begin by giving you some context of the construction sector. Mainly, the problem with this sector is that it's highly polluting. Basically, to the use of the Portland cement in its production generates a lot of CO2 because of the high temperatures needed to the reaction, and the reaction itself releases CO2. So there is a need for more sustainable materials. And on the other hand, we have a problem with the manufacturing techniques, the technologies. The most common is casting using forgers, but this technology has some disadvantages. For example, it's time consuming, some occupational hazard for the laborers, it's a waste generator, and presents also some designs limitation, some freedom of designs. So there are some alternatives in terms of materials. We have plenty of options. Low carbon binders, the most common are supplementary cementitious material and calcium clays, LC3. But the problem with this is it still contains some amount of Portland cement. So in AIMEN, we promote more Portland-free binders, for example, geopolymers and alkali-activated materials, very common. But there are also other options like bio-based cement that I will focus in my speech. And other options are lime and earthen materials that have some specific applications. On the other hand, in terms of novel manufacturing techniques, the most promising is the printing or additive manufacturing. And the key is because you have more automation of the process that brings advantages, for example, reducing the human error and improve safety for the workers. You have more freedom of design to print complex geometries, faster building, and reducing the cost and the materials efficiency. In this slide, I want to highlight which type of bio-based materials can be incorporated into concrete materials. I divide it into 4 different families, so depending on their role. Most important is using bio-based materials to replace traditional binders. And the most common are biomass ashes. These are generated in the combustion of the biomass. And we have different biomass ashes depending on which biomass you burn. But in our project, we collaborate with some local companies that mainly burn trees. But you have other options like rice husk, sugarcane, olive, and so on. Another biomass precursor could be diatomaceous earth from Diatomum microalgae, and it's food that is very, very active. The other function that can be used biomaterials for concrete materials is to use as alkaline activators. In the case of geopolymers or alkaline activated materials, you need an alkaline solution. And the problem with this is it's very expensive and has the higher carbon footprint. So to replace this alkaline activator by bio-based solution is very attractive. One option could be to use the biomass as leaches because they present some alkaline content. And the third one, family or role, could be used bio-based materials as aggregates. There are different options. For example, Exil to use as a source of calcium carbonate to improve mechanical properties, coconut seal or mold seal. We are here in Galicia, so we have a lot of muslins. And for example, in a project called Coral, we are going to study the introduction of muslin cell inside cementitious matrix. And finally, we can also use bio-based materials to add in a small amount, but to induce some specific properties. For example, fibers is important because concrete materials are good at compression strength, but they show a very low flexural strength, so it's necessary to add some fibers. And in the case of natural fibers, are more sustainable. There are different options such as M, flash, and chisel. And you can also introduce bio-based materials as small admixtures. For example, one option is biochar, which is a fancy material that encapsulates CO2. So you are not only a low carbon cement, but a negative cement. Lignin works as a rheological modifier to improve the dispersion and the rheological properties, which is very important for 3D printing. And finally, the last option will be to introduce cellulose nanofibers, which increase the mechanical strength, reduce cracking, and improve the durability of the joint material. Here in this slide is just an overview of our portfolio of our R&D projects. In our sustainable construction group, we have been researching about this success line in more than 10 years in different R&D projects, and have collaborated with different universities, companies, institutions. And our main role in this project is we are the partner that develop the material from waste until develop a high performance functional material, depending on the application, for example, casting or 3D printing, we change the formulation. But our main role is to develop material and to validate with our industrial partner. And some of the applications that we have validated in our R&D projects, as I said, collaborating with our industrial partner in relevant environments. For example, in Geopolar project, we developed some geopolymer bricks, and that we built the small constructing model that you can see in the image. In the same project, with different material, we developed material for pavements. And in Geofeld project, we developed a high porous material that was given by the addition of a foamy agent. It was good for the thermal application properties. In the upper right, we collaborate with a steel plant in the second project, and in this project we developed two solutions, two materials with a high thermal resistance. The application were used in two different solutions, foundry molds and refractory concrete. We obtained very good results in this project. But with this cementitious material can be applied also in alternative applications apart from the construction sector, more related to the environment. It was the case of Life Cooling Adapt project that we developed some cementitious material with absorbent properties that we use to remove pollutant in wastewater treatments. And finally, in the Pérez project, we collaborate with the CEMAT, and we use the cement materials to matrix to immobilize radioactive wastes. And the last 2 or 3 years, more or less, we put a lot of effort into 3D printing. Our main role is to adapt our low carbon cements to 3D printing processes. We have currently 5 projects related to 3D printing. 2 of them are with bio-based materials, Biogens Coral project. Coral is also interesting because we have to develop artificial reefs for the marine environment. And to carry out the work of these projects, we have 2 printers. A small one, very useful to testing experimental materials. It's a Delta model from the Italian company WASP. And the other one is a robotic system. We are setting up right now a robotic cell. We hope that it will be operative in a few weeks or months. And basically, it's a EV robot with a print head from the Dutch company Vertigo with a 2K system that can give us the opportunity, the possibility to add an accelerator and to have 2K materials. And the idea with this robotic system is to pass to the next level, not only be experts in material, but also in additive manufacturing, design, planning, and so on, and printing bigger components such as panels, beams, pillars, and so on. And yes, I want to explain how is our methodology in order to develop printable materials. So we started with the line 2 or 3 years ago, more or less. We don't know exactly how to optimize these materials. We know at that time that rheology was crucial because the 3D printing process can be broken down into pumping, extruding, and building, and all of these phases are governed by rheology. So at that time, we decided to study 8 commercial 3D printing mortars, Portland-based, in order to obtain printability criteria that we will use as a guidelines to develop our low-carb cements. And through different fresh cartation techniques, for example, fold tests, buildability tests, by-cut needle bench here, and we complement all of this work with a rotational realm. So we did this work, and we are now in a point that we know exactly what we need to achieve in order to have a printable cementitious material. We have some criteria in terms of initial flow, buildability, and yield stress. And we also study the evolution of these rheological properties over time, up to 1 hour at 10 minutes interval, and we see the evolution in order to establish also the uptime of our materials. And we complement in this press cartation techniques with a more complex rheology with a rotational rheometer. It's the same that Ricardo saw before. but we have changeable geometries, and we use one geometry suitable for building material, which is called a BMC. That is basically a beam stirred with a cup. We fill with our sample. And with this equipment, we can carry out complex rheology. I can highlight some two of important tests. First one is raw yield stress test. Here we apply to the sample a very, very low constant shear rate, and we obtain a maximum, which is the static shear stress. This stress is the pressure that we have to apply to our cement in order to start the flow. We also analyze the evolution of the shear stress over time. And the second test is even more interesting because simulates the 3D printing process. It's called the 3-interval isotropic test. Here we have three regions of shear rate. First one is we apply a low shear rate, which is when, for example, the cement is before extrusion, for example, in the hopper. Second interval, we apply a high shear rate. In our case, we measure the shear rate of our small printer, the delta one, in order to extrapolate the same conditions, and we measure the decrease of the viscosity. And the third interval, we apply again a low shear rate, and we measure the viscosity recovery, which is related with the buildability and the properties after deposition. And the next phase of our methodology, when all of these previous tests were satisfied, were fulfilled, we pass our materials to the next phase, which is our small scale printer, the delta one. And here we validate our materials through different discrete tests, slab, collapse, and shape stability tests. First one is very easy. You only have to extrude small drops, so-called slags. You have to measure the mass average, and with a physical equation, you can obtain the shear stress, and it's very useful to monitoring the quality of your sample before printing. The second test is the collapse test. As you can guess, you have to print until collapse. In our case, it's a cylinder, and you have to measure how many layers at the time before collapse, and it's also important to check the mode of failure. It will be elastic or buckling, and depending on that, you can change your formulation. The last one is shape stability test. You have to print a standard part, and in this before collapse, and you have to check the stability of the extrusion, the dimension of the layers, the width, the part, and so on. And finally, it's also important to check mechanical properties because we are talking about building materials, so durability and mechanical properties are important. And in the case of 3D printing, it's also important to analyze the anisotropic, because the 3D printing generates some anisotropic depending on the printing direction. So this is something that we study in our projects. We printed 3 different slabs in the 3 different directions, X, Y, and Z. And we cut each slab into specimens, and we carry out a compressive and flexural test. And we observed that in terms of compressive, there are no significant difference, but in terms of flexural, we saw that the Z direction is the lowest, following by the Y, and the X is very, very, very close to like if you manufacture with a traditional casting method. And in this slide, I just want to highlight some of our printable materials developing in our R&D project. In the upper left is a printable Portland cement that we use as a reference, as a benchmark. A metakaolin-based 3D geopolymer. Metakaolin is not a waste of a product, but it's more sustainable compared to Portland cement, and I just want to highlight the mechanical strength, 15 megapascal, which is good for a 3D printing material. In the bottom left, it's our first geopolymer. It's a construction demolition waste based 3D geopolymer that we developed in the framework of Geo's 3D project. And in this material, the mechanical strength were quite good as well, 30 megapascal, more than enough for structural application, but I just want to highlight the waste content over 70%, which is a very good result to be in accordance with the circular economy. And the upper right, it was our work that we collaborate with the Ricardo University. We developed two different materials, a lime-based 3D cement and an earth-based 3D cement. And this material possible present some low mechanical strength, but with this adaptation to the 3D printing, there are some applications that we can find and that could be useful to apply these new materials. And finally, in Biogen's project, as I said before, we are trying to optimize a bio-based 3D cement using biomass ashes. Well, we are very close. In this image, we are carrying out the collapse test, and the material withstand 25 layers. So we need to improve a little bit the buildability without compromising the open time and the suitability. But I hope in a few weeks or months we will have the final formulation. And this project, Biogens, well, it's an important project, European project from the program Horizon, and it's structured in 5 different pillars. Functional bio-based material, which is mainly carried out by us, by AIMEN, but there are some pillars like generative AI design, custom AI systems, digital. And finally, the demonstration that will be 3 smart living labs. The main role of AIMEN is in the developing of the functional bio-based materials, and also we are going to help with the final demonstration. So our task can be divided into the diagram that I show in the right. We start for the raw materials that will be some biomass ashes. In this phase, we characterize through different techniques, chemical composition, crystalline phases, amorphous contact, granulometry. After that, we start with the activation. We try different strategies, different alkaline activation with different solid liquid ratio. Once we have an optimized binder with good mechanical properties and reactivity, we start with developing a mortar. We introduce some bio-based aggregates in order to have a mortar. And the next phase that we are right now is to improve the printability. So in this phase are very important, the heterological mixtures. So we are trying different strategies using superplastizers and isotropic agents, fibers as well, in order to induce the good printability properties. And we hope that we will have our basis printable mortar very soon. And the next phases, the idea is from the mortar to adapt to 3 different solutions. And in this phase, it becomes important the functionality. So the idea of the project is to obtain 3 different products with 3 different functionalities. One of them is CO2 absorption. This will be given by the addition of biochar. The second one is photocatalysis to remove pollutants in air. This will be given by the addition of titanium dioxide. And finally, to induce on thermal comfort properties by the addition of base chain materials. And the idea is to test and to show these 3 products in different demonstrators. These demonstrators will be located in with different climate conditions. The smart living lab one will be located in Madrid with a dry climate. Second one will be located here in Galicia, it's an Atlantic conditions, high humidity. And the third one will be located in Sweden, in Gothenburg, which is, of course, a colder country. That's all from my side. Thank you very much. For the questions.
Okay, so if you wish, please scan this QR code for the questionnaire for giving us feedback on this event. So now there will be for the online participant, that's all. If you have some question or something on the questionnaire, we can then just forward it, or other questions that you will have, we can forward them to the speakers. And for the participant in person, now there will be lunch, and then there will be a visit to AIMEN. Thank you all. I think many of you have already signed the form. If you haven't, please do it. This includes also the participant from the consortium. Please